this. So, good afternoon, everyone. My name is Clint Ricker. I'm a technical lead with Cisco working in the service provider video business as an architect and developer. And I'm here to talk about application renovation with Couchbase. So, our experience in taking an existing application and migrating it over to Couchbase. So, a couple of background points. Just to explain, so the product that I work with at Cisco is called the VSRM, which is a Video Session and Resource Manager. And it enables broadcast, on-demand, and hosted DVR video. And what that basically means is when you're in your home and you're pushing buttons on your remote, we're in the middle making all the stuff happen, helping get the network set up to play back your content. We also do like a hosted DVR solution, like a hosted TiVo thing. We're deployed at cable companies around the world, and we do pretty large scale. Last year, kind of conservative estimates is we're doing well over 100+ billion sessions a year on our platform. We've been using Couchbase in production for a couple of years as the backing for some of our applications, especially most prominently the hosted DVR application. But what I'd like to walk you through the story is how we came to use Couchbase and what it looked like renovating an existing application with Couchbase. So our story, the background here is a pretty common one. We found ourselves in the very good position of having a very successful product. It was deployed, it had very good market penetration. The customers were very favorable towards it, but it was starting to show its age a little bit. The customers liked the efficiency, they liked the reliability, they liked how easy it was to run, but the industry was starting to change. Protocols were changing from binary to HTTP type of REST services, and we primarily work in the cable industry. This product's primarily deployed in the cable industry, and that was going through several rounds of transformations as well. The servers were typically deployed on the city level with servers deployed in the city or even in several servers dedicated to a city, and those deployments were starting to collapse into regional and national data centers. And additionally, it was also the switchover that was starting to happen as things were changing from physical servers to virtual servers and from virtual servers to cloud servers. So when the story starts, we were selling our product as a 1U appliance. We took a stock Dell server, installed Linux as an app, and shipped it to our customers, kind of the very typical appliance model. There are a few problems with this. The first one was that this is a Dell server, and Couchbase had recently launched the UCS product line, which has become very successful. But shipping, when you're Cisco and you're shipping on your competitor's hardware, that tends to not be looked upon internally very favorably. There was also some weaknesses with our model that we're starting to show. Management was streamlined, but there's no centralized management. Scaling out to lots of customers started to require a lot of per-server administration work. And the physical hardware was starting to show its age, and customers were struggling with hardware failure rates, disk failure rates, et cetera. And this is a before picture of our application from the internals design of our application. I'm going to skip over what most of the acronyms are, but basically we're a big believer. Our software itself is shipped as a platform with lots of modules, and so if you want to run in one way, you activate a certain set of modules to deliver the services that you want. And we were also using a homegrown database called Element Manager, which is local in memory, persistent to disk. Very fast, very flexible, very lightweight. We developed it because when the product was launched, there just wasn't a distributed database that worked for us. SQL was too slow. The relational databases of the time were too slow. NoSQL was barely in its infancy when we started, and there just wasn't a database that really fit the performance requirements that we had when the product was started. And this was an overview of our scalability model. So we externally sharded the incoming clients into groups of about 100,000, which were statically assigned to a specific server that had its own local database, its own local management, and then network devices that were controlled by the server were also statically mapped to it. Very scalable. I mean, this works very well to get to very large loads. It's just that, as management of this starts to break down at scale, it becomes tedious to manage, 10 million, 50 million subscribers in this model, having to shift subscribers from one server to the other to rebalance. That sort of thing just starts to become very inefficient at scale. So, like the television show Love It or Leave It, the question arose, do we remodel our application or do we start fresh? If you're buying an old house, there's a phrase sometimes used which is like, does it have good bones? Like, is there something worth keeping in this house? And it's the same thing if you're thinking of taking an older application and migrating it. Does it have good underlying infrastructure that'll carry it through the next several years? Or is it better just to start again and use your experience to guide you along and make something better second time around? For us, we looked at our product and we found a lot, and we liked a lot of it. We thought the underlying design was very strong, and so that was a good reason to keep it. For us, the pluggable architecture, the core components, adapters, it had held very well. It had been very flexible and helped us be successful for several years, and we thought that our design of our product was good and would hold forward for a while longer. The other thing we had to consider was that we had deep customer entrenchment. There's a mentor of mine has the saying, God created the world in 7 days, but he didn't have an install base. And we had lots of customers and lots of large deployments. We had operations teams that were used to our product and the way it worked. We had customers that were used to it. And there was also a huge amount of customization that had gone into our product to make it fit into the customer's environment. Lots of working with their specific software, lots of hardening test cycles to get to our level of reliability. And our algorithms were very complex and with lots of support for a lot of the customer tweaks and the policies that they needed built into there. So we decided to push on, but here's some reasons why you may, the inverse of that of why if you're coming at this with an older application, why you may decide that it's better to scrap it, better to leave it and go go start a new development cycle or go find another path. If you've not been comfortable with the design of your product, it's probably throwing a distributed database into the mix isn't going to help you on that. If your product is easy to start from scratch, it may not be worth migrating. If you don't have a lot of customers that are so, it's maybe worth just starting again and seeing if you can do something that may get more customer stickiness the next time around. And if you've got a huge amount of technical debt, one thing that we discovered in this process is that when you're doing a major overhaul like this, technical debt comes due very quickly. And so if you've got a lot of it, you may, want to resolve that before you go overhaul your application. So, renovation. So it's time to get out our hard hats and get to work. So conceptually, we viewed this transformation as a move from a local database providing shared memory to our from a local database to something that provided to a distributed database that effectively providing a level of shared memory to our application. And by doing so, that enables our application to run then as a single cluster as opposed to several different standalone servers. So why Couchbase? Why am I standing here instead of at a Cassandra conference or a Mongo conference? And the answer to that, we looked at a lot of databases. And we went with Couchbase for a few reasons. And I think if you're using a standalone application that you're migrating to Couchbase, I think migrating to a distributed database, Couchbase is a very good fit for that for some of these reasons. The first is you have very strong consistency. And if you've got a standalone application that's not using a remote database, a distributed database, your application doesn't know about inconsistency. It writes to a variable, it reads what it gets back from a variable. It's never had to deal with inconsistency. And Couchbase is very good about modeling the same type of consistency that you get from a standalone system. For us too, the type of application that we have requires a strong level of consistency. We do a lot of accounting type work. We do resource accounting and bandwidth accounting, and so consistency for us really is everything from an application perspective. And Couchbase has very strong consistency on its get-put operations. It's also very reliably, we love its reliable low latency. We do channel change requests, and that's something that you can't be too fast on. Couchbase is very reliable on how fast that it returns. We see very consistent, 500 microsecond response times from Couchbase, even at very large scale, and being able to count on a very reliable level of performance from a database is very crucial. And it has to scale. I mean, that's we haven't migrated everything we haven't just migrated all of our load over to Couchbase, but as I mentioned at the beginning, we do over 100 billion sessions a year on our platform, and we need a database that we can trust will get us to there in a distributed system. So now to walk through, start getting into the details of how we did this. And it actually ends up that this isn't actually all that difficult. The crux of the work was we added a component called DB Manager that implemented an an application API, facing API that implemented your common calls like get and put and delete and that sort of thing. And then we added an adapter to that talked to Couchbase. And once we had that, we simply taught our internal storage layer to use the new API. And as easy as that, the state migrates over. Well, almost as easy as that. There's a whole bunch of breakage then you have to go clean up. But it really isn't that difficult of a migration process. To walk through some of the underlying concepts, so in doing this, we have, so this is some of the data model transformations that we had to do. So we deal a lot in session data, and so we were previously storing those as in-memory C structures, and then in our local database. Those now became Couchbase keys. One per session, one session ID equals one Couchbase key. Our component data models, which have held our application configuration and our application state, those were in the local database. Those were changed now to be one Couchbase key basically per table. The session data we peeled off into a key per session ID, and then counters. We had a lot of counters in our data model that those we stored as individual keys because Couchbase has this nifty little where you can just tell a key to increment or decrement, and so having counters as separate keys enabled us to do this. And then our various sorts of raw memory things or C structures and that sorts of things. We're coming from a C++ environment, so that was actually pretty handy because you could just mem copy everything onto your, basically mem copy it over to Couchbase. The Couchbase also in their APIs for like Python and Java and so forth handles that, to where the object automatically gets saved to Couchbase without doing a whole lot of work on it. Something that you have to really pay close attention to when you're taking an existing application, or really when you're doing a new application, is also your data sizing. A few things to consider on this. Smaller keys have lower latency, and that's just laws of physics. It takes, we're talking, a couple of hundred microseconds for an operation, for a get or put operation to Couchbase. Most of it is how fast can the data be transferred from the wire. And so if your objects are 1K, they'll transfer a lot faster than if they're 1 meg. The other thing, one other consideration is that you have a hard limit of, and this isn't Couchbase, this is just physics of dealing with a distributed database, of how often you can mutate a specific key. Because if you think of it in terms of Couchbase, you get the key, you update it and you write it back, and you get it and update it and write it back, and that, so the latency of that, half a millisecond, a millisecond, and you're limited to 1,000, maybe 2,000 a second times that you can mutate a key max, and so you have to take that into account in your data modeling, and if you do large keys, then that rate goes down, and you may not even be able to do 1,000. You may only be able to do 500 or so forth a second on them. But then the inverse of that is that if you're trying to write a set of data to the database, you have to think through what happens if the database or the network dies, or your server dies right after, write 3 out of 6. And so you have to either have some sort of transaction layer that you run at your application, or alternatively, if you model your data so that one key contains what you need to write, then that is going to be an atomic operation, and you don't have anything to roll back if the server goes down afterwards. So there's not a perfect answer there, and you kind of have to just play with your data set and see what makes more sense. Do you do a larger? Can you handle a larger write in order to not have to deal with transactions, or do you do smaller objects and have more efficiency from that, but then have to deal with transactions? A few design rules that we followed. We wanted to have very reliable, consistent behavior towards the end user. And so we had a rule that all real-time operations use get-put operations. Those are pretty much infinitely scalable and very low latency. We reserved views for maintenance operations, and there's two reasons for that. One is that they are a more finite resource on Couchbase, especially the higher levels of consistency you need on views than the more finite the rate of view queries you can do. But the second is that, as I mentioned in the beginning, our application itself requires a very high level of consistency, and the views themselves on Couchbase, those are somewhat asynchronous to your get-put operations. And so if you're needing data consistently, if you're needing a consistent read on your data, you have to read it from a key, not from a view. The other design rule we had is that all database calls goes through an abstraction layer. This is just, it let us enforce best practices on our application developers. Gave us a single point of logging, troubleshooting, debugging, that sort of thing. And it gave us a way to play around with different databases, put Mongo in there and see how it does, put Cassandra in there and see how it does, and swap things in and out, plug them in and out, and once if you have a decent abstraction layer, swapping over to another similarly structured database isn't all that much work, and you can do some head-to-head comparisons with your own application. Another thing to consider as you take a existing application and move it to use Couchbase, pessimistic locks are a reasonable enough replacement for mutex, but they provide serialization only, not ordering. So if you have calls 1, 2, 3 go in for the same key, it's very possible. Call 1, if it went in first, probably would get the lock, but then when it releases the lock, call 3 may be the one that picks it up first. You can use optimistic locks for read efficiency, but they're not going to really give you much efficiency on writes if you're needing to optimize that. For queries, what we've learned over time is you want to be very intentional on what data is being indexed, and this is especially true if you're coming from an existing application that automatically is generating all sorts of data. You want to be intentional on what data you're exposing, what data is indexed, so that it's very clear as to what data you get out of given queries. As I mentioned before, queries have weaker consistency. The flip side of that is that it's how Couchbase gets a lot of the scalability out of it, but you have to understand that and not expect strong consistency out of a view read. And it's a limited resource, especially if you're doing stel equals true. If you're asking, your Couchbase can't magically run a scan across 100 million records and give you a consistent read on that at an infinite number of operations per second. That's almost as much of anything a law of physics problem. Another thing that what we've discovered a little bit with Couchbase too is that having a very low latency key value store, um, when you move to a distributed system, to a clustered system, you get Couchbase almost becomes a little bit of like a Swiss Army knife for your clustering. And one thing that's a little bit different from us to some use cases is we develop an application and we've got to like pick it up and we've got to put it in someone else's network and keep it running. And so we tend to be very adverse to having a large number of supporting services, because for each supporting service we have, if we deploy RabbitMQ or Zookeeper, or, all these sorts of things, we have to teach a customer how to run it on their network. We're responsible every time it fails, it looks poorly on us. And so we tend to try to be fairly parsimonious about the external dependencies we put on our application. And what we discovered over time is that Couchbase, for a lot of things you do in that cluster, it provides, it lets you do things. It lets you do a lot of these things pretty simply. We use it as a lightweight directory service where nodes will publish their identity to a well-known key that other nodes can look up. We do simple distributed queues where we just append to a key and then we can read them off of the key as needed. We also have for some of our maintenance operations, we have a master election process, which is just simply we have a specific key that we're doing a get with lock, and whoever got it with the lock is the master, and he keeps refreshing it, once a minute. And if he dies, the lock will time out after a couple of minutes, and someone else will get it. It's not really workable for something where you need like if you need like millisecond or a second changeover on a node failure. But for maintenance operations that we can survive for 5 minutes without, it's very effective, and it avoids us having to deploy a whole nother suite of software to provide these functionalities. I wouldn't say on any of these that they're replacements for like Zookeeper or RabbitMQ or any of those, but Couchbase gives you you can build these on Couchbase and get the functionality that most people use out of these without having to deploy a separate software. But it is just a limited version of these, admittedly. Some danger zones. You need to watch out for key contention and break apart keys if necessary. And this is especially true if you're doing a lot of locking reads, locking writes. You have to really think through how your application is going to perform when you get a lot of people trying to get a locking read on a specific key. Break apart keys if necessary, or even better yet, redesign to avoid. Distributed databases require robust error handling. This was the main point of technical debt we had, was that we were coming from a local database in memory. It was a write was guaranteed to succeed, a read was guaranteed to succeed. We didn't have much error handling in our code around those, and that was something that we had to add in and had to take care of to catch up on. Also, if you're taking standalone servers that are taking a sharded amount of load and then creating a big cluster out of them, then you have to adapt your testing accordingly. And one of the things that we've discovered, we came across, is that you have to test your error handling and your edge cases at the new level of combined scale that you have, because the cluster as a whole is now facing it off of the aggregated load, not as the 100K per server max. And so now, like any good renovation show, we have our grand reveal. So this is our before Picture for Couchbase, for VSRM before we started using Couchbase. And our internal design evolved where we added the DB manager and the Couchbase adapter over on the bottom right-hand corner. And this is our scalability model before Couchbase, where each node is taking roughly 100K subscribers, handling a small set of network elements, and locally managed, local database, etc. And this is what we've ended up with, what our architecture looks like today. So now after our transformation, we have horizontally scalable virtual machines. We provision them on Rackspace, Amazon, whatever, using heat templates or whatever to provision them on the system. We could do things like auto scale up and down as needed. And we have horizontally scalable VMs fronted by generic HTTP load balancers. Centralized management, actually I guess a better is, you can manage the cluster from any of the nodes. And then we're no longer having to map clients to specific instances of our service or devices to specific instances of our server, but we just have a load balancer in front of it. Any instance of the software can handle any client that can handle any request to or from a device. It also has opened up for us to do other deployment designs where instead of doing single unified VMs, we can also break apart into different modules and scale our adaption layer separately from our application layer or from our resource management layer. And that's all I've got. Any questions from the audience? So, well, it's never done to be. I mean, so prototype was about 4 weeks. All told, background of about, it's a kind of background work for us in the team, but probably about a year total worth, although segmented into, a few months here and then go off and focus on, on stuff that pays the bills immediately. But yeah, probably about a year so far of, kind of focused work altogether. Yes? So on the before or after? On the after? Yeah, so on this, your database provides the high availability, right? So Couchbase itself builds in redundancy. You can have n+1, n+2, however many extra servers you want, and you can keep, 1 extra copy of your data, 2 extra copies of the data. And then if a node itself goes down, your in-flight sessions are at risk, but anything that's made it over to the database is available to be picked up on from a different node. Did that answer your question? So we haven't yet deployed with so you're talking cross data center wise. So we haven't yet deployed with XDCR. The problem there's a couple of reasons for that. The main one is that our application itself requires very, very high levels of consistency. If we If we get out of sync within our application, like, so it's very possible, if our application were to get out of sync, then it's possible that we could tell someone makes a channel change request, and we tell them to go to the wrong channel, one that's already been in use that we had forgotten about because of the lack of consistency. And then you get nasty things like, kids trying to tune to Disney and getting adult content. And so we're still, we're kind of dipping our toe into the XDCR because it's inherently an asynchronous thing. And so for us, XDCR is less about active data center and more of a disaster recovery model where, if a data center goes out, you will probably have a little bit of an outage because in our mind it's better to be out than to stream the wrong content. FCC doesn't like kids getting porn on Disney. But we can still provide, a few minutes after data center 1 fails, then data center 2 can safely take over without any risk. Yeah.
What kind of multi-tenancy are you currently supporting?
So we support multi-tenancy. We support multi-tenancy on the application level. But that's just basically that the service calls coming in can say, oh, you're for tenant A or you're for tenant B, and segregate accordingly.
There's a different kind of multi-tenancy. I'm used to for the same cluster, you're running multiple applications.
Oh, okay.
I'm not saying
Yeah.
of course that's
Yeah. Okay. We fully support it, and we fully, I think from sort of our design perspective, we kind of look at the nodes as kind of compute nodes. Like any node can they all have the same software on it. It's like any of them can take the incoming message, call the appropriate function calls and return. And so one other thing that I've really liked about Couchbase, although they're evolving beyond this in 4.0, but it was the single node type, which is that it's simple to manage when you've only got one node type, and you just add additional nodes to.
So let's say Couchbase and a non-Couchbase based application, there are so many, right? And you're running on the same cluster, or you're running on different dedicated cluster right now.
Um,
Like say Hadoop, right? So let's say Kafka, and say Couchbase, say Elasticsearch. Are you running those applications on the same cluster, or are running on separate dedicated cluster right now?
so for our primary application, we're only using Couchbase. There is some analytics work that is, from because we generate tremendous amounts of data, and sometimes like the log scraping and turning that into meaningful data we use Hadoop, but that's sort of as a sort of separate subsystem, largely external to our application. We don't deploy it on a combined thing now. So, any more questions? So, okay. Well, thank you, everyone.